All right, finally. All right, fire away. What do you want to talk about? Anyway, ask a question. Ask a question. Who wants to go first?
First, maybe not a question, just the difference between flux and luminosity, just so I have it understood. You know, now I'm freezing on it, but flux is per square
Per square meter per area. Yep.
And luminosity is total.
It's just the total coming out of all the square meters. Yep. So yeah, so a star's luminosity is add up all the energy coming out of every square meter of its surface. Its flux is how much luminosity is coming out of each individual square meter of its surface. So if I had two stars and they were the same temperature, they would have to have the same flux because that's what controls how much energy is coming out of each square meter. But if one of them's bigger, it'll have the higher luminosity because it's got more square meters sending out that same amount of flux. Yep.
So I understood it.
Yep. Cool.
Can we go over the astronomical distance ladder?
Sure. And so I can get to it quicker. Which chapter was that?
Chapter 3.
Chapter 3. Okay. So up here. Course it is. Astronomy 260. Presentation 2. Chapter 3, you said, right? Okay. So the basic idea behind the distance ladder is that it's a way of building up our knowledge of distances to faraway objects based on typically standard candles, typically objects whose what is this? Okay. Hang on. Somebody set this so that it displays this. Here it is. Alright. So I guess usually it's based on standard candles, but it starts with radar and parallax. So in other words, the first thing we need to know is how far is Earth from the sun. And the way we do that actually is with radar. We don't bounce radar off the sun, but we can bounce radar off Venus and Mercury and Mars and so forth. And that lets us precisely determine how far away Venus is at that moment. And because you can time how long it takes the radar signal traveling at the speed of light to go from Earth to Venus back to Earth again. So that tells us how far away Venus is at that moment. And we can figure out how far away the sun is because we know how big Earth and Venus's orbit are relative to one another. So if we know how far away Venus is, we can infer how far away the sun is. So that gives us the astronomical unit. So that's like the first rung on the distance ladder. Then we want to find out how far away other stars are. can't bounce radar off of other stars, they're too far away. On the other hand, we can use parallax. We can use the fact that Earth is going around the sun, and so our line of sight to stars changes as we orbit. And if we measure how much our line of sight shifts back and forth, if we measure the angle on the sky that the star's apparent position is shifting back and forth relative to much more distant stars, then we can figure out how far away those stars that are close enough to measure in this way are. And so half the shift is called the parallax, and we define 1 parsec to be how far a star would have to be away from us for the parallax to be 1 arcsecond. And then, once we measure the parallax in arcseconds, if we just take 1 divided by that, that's the star's distance in parsecs. So radar and parallax are our 2 direct ways to measure distances. Once we have, then we use standard candles. So the most important type of standard candle originally were the Cepheid variables. I'm going to do this business of switching to these points. So Cepheid variables are stars whose brightness goes up and down, up and down. They're pulsating variable stars. And there is a period-luminosity relation. There's a nice, well-defined relationship between how long it takes the star to go through 1 full brightness cycle, brightest to dimmest back to brightest again, and what its luminosity is, what its total amount of energy it's emitting every second. Since it's variable, what we're really going to see is average luminosity over the whole cycle. To calibrate it, we had to measure, we had to find stars that were Cepheids close enough to us to use parallax, and then we could, from that, determine what their distances were, and then from their apparent brightnesses, infer what their luminosities were, what their true luminosities were. That allows us to calibrate a graph like this, and then that's what allows us to measure distances to relatively nearby galaxies, because if a galaxy is close enough to us, we are able to measure Cepheid variables in it. So that's what Hubble did in order to find the distance to the Andromeda Galaxy. He identified a Cepheid variable, right there, the ones that's far next to it. He measured how long it was taking to go from brightest to dimmest back to brightest again. He could then use the period-luminosity relation to find out what its luminosity was. And from its luminosity and how bright it looks from Earth, he could calculate the distance to the Andromeda Galaxy. And he showed that that is way too far away to be part of our galaxy. And then he started doing that in other galaxies as well. So for galaxies within about 100 million light years of Earth, the Cepheids in them are able to be used to measure their distances. Our telescopes are able to do that. But then there's these other distance indicators too that we can use on galaxies that are too far away for us to measure Cepheids in them, because they're so far away, even Cepheids aren't bright enough for us to measure in those galaxies. So then we turn to things like the Tully-Fisher relation, which tells us that the faster the stars in a spiral galaxy are moving around the center, in general, the more massive the galaxy is, and the more massive the galaxy is, the more stars and so forth it has, so therefore the more luminous it is. So there's a relationship between a galaxy's luminosity, which is really what this axis is telling us, and the speed with which its stars are orbiting the center of the galaxy. So we can use that to find distances to spiral galaxies that are too far away to use Cepheids. How did we calibrate it? Because there are some spiral galaxies where we can make these measurements and they've got Cepheids in them. So we can calibrate this using nearby spiral galaxies. And then we can use it on more distant spiral galaxies and infer how far away they are using this relationship. And so what it comes down to is the reason we call it a distance ladder is because it's kind of like rungs on a ladder where we use parallax to measure distances out to, this says 500 parsecs, we can do better than that now, this is an old graph. With current technology in orbit, we can go better than this, but we can measure parallax to stars close enough to us in our own galaxy. Some of those are Cepheids, so we could calibrate the brightnesses of Cepheids, the period-luminosity relation, and that allows us to measure distances out to about 30 megaparsecs, about 100 million light years away. And then the Tully-Fisher relation and the fundamental plane, which is a reference to which is a fancier version of the Faber-Jackson relation, which works for elliptical galaxies. That lets us use entire galaxies as kind of like standard candles, and we can get out to about 300 million light years, about 100 megaparsecs. And now, the best we have these days for the most distant galaxies is type 1a supernovae. Those are standard candles where we can measure distances to billions of light years away with those. So it's a ladder because each one needs to be calibrated by the lower step on the ladder series.
Is there a reason that Cepheid variables only work at 1 parsec out?
Oh, no, I believe what that's referring to is I think that the closest ones are about a kiloparsec because they're relatively rare stars. So I think it's simply that the closest one's about a kiloparsec away. Certainly it would work if one was closer to us there. I think that's just a practical limit there. That's a good question. Yep.
What is the Faber-Jackson?
The Faber-Jackson relation. What is the Faber-Jackson relation? That is for elliptical galaxies instead of spiral galaxies. The idea with the Faber-Jackson relation is elliptical galaxies don't have a well-defined rotation like spiral galaxies do. Elliptical galaxies, the stars are moving every which way in them in all kinds of angles instead of being in a nice flat plane where everything marches around in the disk in a nice organized rotation pattern. Elliptical galaxies are more like swarms of gnats in that the stars, they move on nice orbits, but they're at every angle. And so there's no nice well-defined spin to an elliptical galaxy, no nice overall rotation. The stars are moving this way and that. But the more massive the galaxy is, the faster the stars have to be moving in order to keep from just all falling into the center. So a more massive galaxy has faster moving stars, which will give us a bigger spread of Doppler shifts when we measure its spectral lines. And so the Faber-Jackson relation is a relationship between how fast the stars are moving in the galaxy based on the widths of its spectral lines, the Doppler shifts of moving towards us and away from us in its spectral lines, and the star's luminosity. And again, the reason that should be is because a more massive galaxy is one that has more stars and therefore is more luminous. And so the Faber-Jackson relation is a plot of the star's brightness of the galaxy, the brightness of the galaxy here on the x-axis, and a measure of the spread and speeds of the stars on the y-axis. And so it too can be used like the Tully-Fisher relation to determine distances to faraway galaxies. Because galaxies are much brighter than individual stars are. So you can use galaxies as standard candles for much greater distances than you can use stars, simply because a star needs to be bright enough to be seen from far away. And you can see galaxies from further away than you can see individual stars in galaxies. The exception being type 1a supernovae, the white dwarf supernovae. Those are spectacularly bright, and so you can see them out even in galaxies that are so far away that it's hard to see the galaxy. It would be easier to see the supernova than it can be to see the faint fuzz of galaxies.
I want to move on to chapter 4.
Okay,
Ask
chapter
about,
4.
Wimps and machos.
Wimps and machos, yes. Wimps, machos, dark matter, chapter 4. Okay. All right. Before I do that, I'm going to see if I can get this displayed nicer to me because it's a little hard for me to keep going back and forth between displays that don't look the same. So let me try some. Let's see. It's dangerous. They're trying to get clone displays, built-in display plus digital television. It's a miracle. Okay, it worked. Okay, so you want to talk about chapter 4, wimps and machos. All right, let's do that. And now, what's this? Now it doesn't look like it. Right, no. So, of course, wimps and machos are two candidates for what dark matter could be. And so machos, do you remember what machos stands for?
Massive, compact halo.
Yeah, macho stands for massive compact halo object. So the MA is from massive, compact is C, halo object is HO. So massive compact halo objects. Machos would be matter like you and I are made of. So in other words, it could be dim red dwarf stars that are distributed in the galaxy's halo. It could be planets. It could be what do I want to say? It could be like white dwarfs or neutron stars or black holes. All of those things are things that don't emit a lot of light compared to how much mass they have. So in other words, if there was lots of white dwarfs in the halo of our galaxy and in other galaxies, there could be a lot of mass there without a lot of light because white dwarfs are not very bright. They're not nearly as bright as a star is. A 1 solar mass white dwarf doesn't emit nearly as much light as the sun does. So a halo full of white dwarfs wouldn't emit nearly as much light as a halo full of suns would. So it would count as dark matter simply because while it does give off light, it doesn't give off nearly as much light as normal stars do. And so one idea for what the dark matter could be would be there's lots of white dwarfs, neutron stars, and black holes, and maybe brown dwarfs, maybe very dim red dwarf stars in the halo of our galaxy. So they add up to a lot of mass, which gives our galaxy a flat rotation curve and other galaxies, but they don't contribute a lot of light. And so they're dark, not in an absolute term, but relatively dark. They're dark relative to more massive stars. So we searched for machos using gravitational lensing, because occasionally a macho would pass in front of a more distant star, like in the Large Magellanic Cloud, a satellite galaxy of our own. And we found some, but not nearly enough to account for as much dark matter as there is. And that leaves us with what is currently the best candidate for the dark matter, weakly interacting massive particles, WIMPs. And the idea behind WIMPs is that they would be similar to neutrinos, which are particles that do not interact electromagnetically. They don't feel or generate electric and magnetic fields. They only feel gravity and what's called the weak nuclear force. But neutrinos are not a good candidate for matter because they're what we would call hot dark matter. They tend to be created moving near the speed of light, and particles moving near the speed of light wouldn't be able to clump together gravitationally enough to be forming halos around galaxies. So the guess is that the dark matter is particles that are similar to neutrinos, subatomic particles similar to neutrinos, but much, much more massive, so that they're moving much more slowly and are able to clump into halos gravitationally. And so that's our current, we've never detected one, so we certainly can't claim that we know this for sure, But our best guess is that's what the dark matter is, because it would fulfill needing lots and lots of mass that isn't emitting light so that we can detect it.
What's the, sorry, this is going back to chapter 3. What's the period luminosity?
The period-luminosity relation is the fact that for Cepheid variable stars, those special variable stars, there is a distinctive relationship between how long it takes the star to go from brightest to dimmest back to brightest again, and how luminous the star is, such that this is the period luminosity relation right here for so-called population 1 Cepheids, ones that are in the disks of galaxies instead of the halos of galaxies, or ones that are in spirals as opposed to dwarf galaxies. The other ones are called population 2 Cepheids. The idea here then is that notice that a Cepheid with a period of 3 days is about 1,000 times more luminous than the sun. A Cepheid with a period of 10 days is more like 3,000 times more luminous than the sun, and so forth. So the longer the period, the more luminous the star. That's the period luminosity relation. The reason it happens is because Cepheids, in a sense, are kind of like ringing. They're pulsating like a bell does if you strike it. So if you strike a large, massive bell and a small, not so massive bell, which one vibrates faster, the big one or the small one? The small one does, right? That's why a small bell, you hit it and you're like, ding! And then a big bell, you hit it and it's like, bong! Right? Stars are similar. A bigger, more massive star rings more slowly than a smaller, less massive star. And a bigger, more massive star, these Cepheid variables, will also be more luminous. And so the reason why higher luminosity goes with longer period is because those stars are literally larger, and so they ring more slowly. They take longer to go through one cycle. It's kind of qualitatively what it comes down to. So the idea then would be, if I observed a Cepheid variable in a distant galaxy, and I saw that it was going from brightest to dimmest to brightest once every 3 days, I would know it was 1,000 times more luminous than the sun, and that would be the piece of information I needed to figure out from the apparent brightness and its actual luminosity how far away it is.
And they calibrated this using parallax and nearby?
Yes. Originally, there had to be a statistical technique used. But now that we have satellites in orbit specialized for finding parallaxes, unlike in the past, there are now, because we can use parallax further away than we used to be able to, there are Cepheids where we can directly measure their distance with parallax. And so this ultimately now is calibrated by observing Cepheids that are near enough to use parallax on, so that we can independently figure out their luminosities. In other words, in that case, we measure their brightness, we know the distance, and we calculate its luminosity. We know the distance from the parallax. Then for ones which are too far away, like in other galaxies, for us to be able to use parallax, stars in other galaxies are way too far for us to see the parallax. Then we can say, okay, I can't use parallax, but I can use the period luminosity relation and the star's apparent brightness to figure out what its distance from us is. They were using an antenna
Yeah.
that was designed to talk to the Telstar satellite. So they were not astronomers. They were not trying to study the universe in any way. This antenna was built specifically to talk to a satellite called Telstar. And this was in the early days of satellite technology. And what they found is they were getting a hiss in their signal that they couldn't account for. And they thought at first that there was a problem with the electronics or maybe some other problem with it. They tried everything. It didn't depend on what time of day it was. It didn't depend on where the antenna was pointed. So it seemed to be coming from every direction in space. And then by chance, they learned that other researchers had predicted that there would be microwaves coming to us from the early universe. And two were put together, and it was realized that they had discovered this cosmic microwave background, which is from the time when the universe first formed atoms. The first time electrons ever combined with nuclei, hydrogen and helium nuclei to form atoms, is called, stupidly enough, recombination. The first combination is called recombination, which sounds like it's repeating, but that's not what it means. And that was the cosmic microwave background radiation. So it's coming to us from when the universe went from being opaque, filled with free electrons that were able to scatter photons every which way. A photon couldn't travel very far before being redirected by an electron, to transparent, because once atoms formed, remember atoms only like to interact with photons at very specific wavelengths that can make them change energy levels. Most wavelengths they essentially ignore. So in a cosmic eye blink, the universe became transparent, and that's what we're seeing when we see the cosmic microwave background. We're looking back all the way to the time when the universe was only 380,000 years old to when it had become transparent. We can't see back further than that time in any kind of detail, simply because the universe was opaque, and so you couldn't see into it, so to speak. If you try to look back to a time when the universe was 200,000 years old, you would be needing to look at distances corresponding to seeing the universe when it was still opaque. So as far as we can see is out to this so-called surface of last scattering, where we're seeing the cosmic microwave backgrounds from. That's what we're seeing in this picture, that surface that's about 45 billion light years away from us in every direction when the universe became transparent. We're seeing microwaves from that time. And this is just a representation of them in color. Different temperatures are represented with different colors here of the microwaves. So that's the CMB.
It's negative 270.
Yeah, it's better to think of it, I don't like the way that they use centigrade here. It's better to think of it as being at about 2.7 Kelvin. 2.7 Kelvin above absolute zero, which is what this translates into Celsius.
Will we have to know Arno, Penzias, and the other guy? Will we have to know them by name?
You mean like Penzias and Wilson? You mean you don't know Penzias and Wilson by name? How did you not know Penzias and Wilson? Did I say Penzias and Wilson? Yes, Penzias and Wilson by name? I mean, I don't think I put that in the sheet for you to know that, but you should know Penzias and Wilson just because it's good to know such esteemed people who won a Nobel Prize for finding the leftover microwaves from the creation of the universe. I mean, Penzias and Wilson, right? Penzias and Wilson.
Okay. Did they continue on in astronomy?
I don't think so, no. But they got their Nobel Prize, so that's cool, right?
What was that satellite originally for?
Telecommunications. It was an early television, radio, television satellite. Yeah. So it's Telstar, television star, so to speak. It was a big deal back in the early '60s. There was even a song written about it and so forth. Yeah, because basically, you have to think with each new technology, it's a miracle at the time. So think of smartphones. In '07, when the iPhone came out, here's this miracle in your hand, and now everyone has one. They're still like miracles in your hand, but it's like, oh my God, smartphones anymore. right? When they first came out, oh my God, what is this device? It's amazing. The first satellites were like, oh my God, I can watch a television show live from Europe. That was amazing back then. Now I can just click on the internet and see television from Europe. I watch German television stations all the time. But in the early 60s, it was this huge deal that you could see live broadcasts from, like across the country and around the world, like bouncing TV signals off the satellites.
So I just want to make sure I have this right. Hilbert's paradox. If the universe is infinite in size and age,
Yes.
then the night sky should be as bright as the surface of the stars.
Right? Yes. If it was infinite in size and never changing, so that it was infinite and had always been filled with stars, then that would mean no matter what direction you look, eventually your line of sight ends up on the surface of a star somewhere. So every direction would be a direction to the surface of a star, and that would mean the whole sky would look as bright as the surface of a star. Similar to the way that if you're in a really dense forest, and even this one isn't dense enough, everywhere you look, you hit a tree trunk. This one's not dense enough because here's a space where I can see to the blue sky behind and I didn't hit any tree trunks. But if this forest went on forever, that wouldn't be true anymore. There would be tree trunks absolutely everywhere. There would be no place you didn't see a tree trunk. And that would be our universe if it was infinite, filled with stars, and had always been so. On the other hand, the sky is dark at night, so that means at least one of those assumptions is wrong. So for example, suppose the universe had been here forever and stars were shining forever, but the stars were only in a region a few thousand light years across. Well, then in most directions, you wouldn't hit any stars and you'd just be seeing the blackness of space beyond that, and you would just see a night sky that was filled with points of light being stars, and that'd be it. But on the other hand, we think that the universe is probably infinite in size, or at least it's really large, and that there are stars in every direction. But on the other hand, that hasn't always been the case. There was a time before stars. And the further you look out into space, the further you're seeing back in time, which means that if we look far enough and our line of sight hasn't hit any stars yet, if we're looking along some line of sight and we look far enough, it's never hit any stars, it never will past a certain point because you're looking beyond when there were stars in the universe. You're looking at times before any stars were born. And so that's how we resolve Olber's paradox, is that the stars haven't been shining forever, and if we look far enough away, we see back to a time when there weren't any stars shining, and so we don't see stars in those directions. I mean, those directions are everywhere, but in other words, we can't see infinitely far towards stars in every direction, which means we can miss, basically. We can look and never run into a star in many directions, because eventually that line of sight, not having hit any stars, starts to be going along a region where there aren't any stars anymore because it's that far back in time. So strangely enough, even though you take it for granted that the sky is dark at night, it's actually telling you something profound about the universe, that it is ultimately, it's either finite in size or finite in age. And the answer turns out to be it's finite in age.
I think you alluded to an open-ended question about the age-metallicity relation.
Yeah.
But I think I have a pretty good understanding of it, that just the older stars lack the heavier elements in their shells because whenever they were formed, those metals weren't around.
Right, that's the basic idea, is that right after the Big Bang, there was almost nothing in the universe but hydrogen and helium. There was hydrogen, there was helium, and a tiny amount of lithium, and that's essentially it. That's all the universe had in it. So stars, the initial stars that were born, were made of nothing but hydrogen and helium and that tiny fraction of lithium. Who cares? But that initial generation of stars cooked up new elements by nuclear fusion in their cores, and then when they blew up, when they died, they put stuff that they had made in their cores, new elements, into the interstellar medium. So the next generation of stars was born with elements that had been made by the first generation of stars. And that kept going. Of course, stars don't have, just like people, stars don't have definite generations, right? In other words, it's all blended together. But in other words, what am I trying to say? As you go, as the universe ages, stars keep being born from material that had earlier generations of stars keep adding more heavy elements to it, higher amount of heavy elements to it. So the youngest stars were born from material that had been enriched for the longest time, enriched up with elements from earlier generations of stars. So that's why we see that in general.
And how is that different from the explanation of why there's more lithium in older stars?
It's not completely different. They are related facts.
Okay.
In other words, the same kind of ideas are at play. Just it's a variation on a theme. So there's the five lightest elements are hydrogen, helium, lithium, beryllium, and boron. Hydrogen and helium are primordial. There's some helium being built in stars today, but most helium is left over from the Big Bang, and essentially all hydrogen is left over from the Big Bang. Elements heavier than lithium, beryllium, and boron are cooked up in stars or in neutron-star collisions. Lithium, beryllium, and boron, the way it's different is they are created in the space between the stars, in the interstellar medium, by high-speed particles crashing into heavier nuclei and breaking up apart, and some of the fragments are lithium, beryllium, and boron nuclei. So lithium, beryllium, and boron are being built today in the universe, but not in star cores. They're being built in between the stars by these high-speed collisions. So that means that as the universe has aged, there's been more and more lithium, beryllium, and boron in it because there's been more time when those are being built in between the stars by cosmic rays. And so if that was the whole story, we would expect that for all three of them, the oldest stars had less than the youngest stars do, because the older stars were born when not as much lithium, beryllium, and boron had been created yet. And that's exactly what we see for beryllium and boron. The older the star is, the less beryllium and boron it has. But for lithium, at first, older stars have less lithium in them, but pretty soon you reach this cutoff where no matter how old the star is, it has about the same amount of lithium in it. And what that is telling us